Hello students. So today we are on the last topic of unit 3, that was fuzzy logic, and the last topic of the unit is the membership functions. So in this lecture we will discuss something related to the member function of variety of fuzzy sets. So friends, so the membership function, it basically defines the fuzziness of a fuzzy set of its elements. So elements, they can be continuous in nature, they can be discrete or in nature. So irrespective of the nature of the elements in the fuzzy set, the membership function, it describes the fuzziness of the elements of the fuzzy set with respect to the fuzzy set. So I'm again explaining it. The elements in the fuzzy set, they can be continuous in nature, they can be discrete in nature. So irrespective of the nature of the elements of the fuzzy set, the membership function, it describes the fuzziness of all the elements of the fuzzy set. So generally, membership functions are represented graphically. So lot of ways are there by which graphically we can represent the membership function of a given fuzzy set. Generally, these graphical representations, these graphical ways are triangular way. Triangular way is one of the mechanisms by which we define the membership function. There is one another trapezium way in which we can also define the membership functions. So generally you will see two type of functions, membership functions, triangular function or the trapezium function, in which membership functions can be defined of variety of fuzzy sets. So as I told you that it provides the fuzziness, vagueness of the element, it provides the vagueness. So the standard shape of membership functions are maintained over the years. Generally, these type of membership shapes have been used by the different authors. So fuzzy membership functions are determined by the opinion of the expert, those who are having the expert knowledge in that domain. Say for example, we are getting some information in the form of fuzziness in the in landing the aircraft. So the variety of information which we are extracting, so we will extract it from the opinion of the expert persons, those who are having the experience of that thing. So the pilots, those who are having the experience in that domain, at what wind pressure, at what speed, at what humidity, what is the different scenario which are measurable or which can be quantified in landing or take on the any aircraft. So these type of information is generally captured, abstracted with the help of the opinion of the expert members. So on the basis of the opinion received from the expert person, we generally make the fuzzification of the elements of the fuzzy set. Rather, we can say in that way we will be able to maintain a membership function which will provide the membership value to the different elements of the fuzzy set. So in the same way here, it has been mentioned that fuzzy membership functions are determined by the opinion of the experts, right? So there are several ways to characterize the fuzzification. There are a lot of ways by which we can characterize the fuzziness. In similar, there are several ways to graphically construct a member function that describes the fuzziness. So generally you will see that we will make a graph, and with the help of the graph we will assign the membership value to the different element available in the universe of discourse of the fuzzy set, in which fuzzy set is defined. So here, say for example, we are having a fuzzy set A which is defined over a universe of discourse X, and this can be defined by this way, by an ordered pair of an element and its membership value, where X belongs to the universe of discourse. So the fuzzy set is basically is a collection of ordered pair of the element along with its membership value, right? So here mu ax is the membership function of A. The mu ax basically it gives you the membership value with respect to that set, which can be achieved with the help of the membership function. So we will make a graph. On x-axis we will place the elements from the universe of discourse, and from y-axis we will find the membership value, which we will find with the help of the membership function, and we will draw a membership function in the xy dimensions, right? So here we are saying that the membership function mu x maps x. It gives a value to x, and that value is always in the range of 0 to 1, in an interval of 0 to 1. Here it has been mentioned that the membership function mu x maps x. It will give a value to x to the membership space M. So mu A, this is the membership function. It is the membership function of fuzzy set A. What it is doing? It is just providing a value to the element which is available in the universe of discourse in a range, and that range has been provided by M. So this range can be 0 to 1. If x is having value membership value 0, so we are saying that there is it is not the member of the fuzzy set. If we are giving it a value 1, so we are saying that it is having the complete membership value, right? So here 3 basic features are there that are involved in characterizing the membership functions, and they are core, support, and boundary. So students, just see the diagram which is here. It is depicting some information to us. We are working on 2 dimension. On x dimension, we are having various elements of the universe of discourse. They may be discrete or they may be continuous. So irrespective of the nature of the elements of the universe of discourse, which we have plotted on the x-axis, on y-axis we are simply finding the membership value of all these elements. So here we are having a graph, and that graph is basically a trapezium. It's a trapezium. So this graph itself is representing the membership value to all the elements of the universe of discourse with respect to the fuzzy set A, for which this membership function has been defined. So say for example, there are some elements in universe of discourse and its value lies here, in which I am pointing it. So here for those elements the membership value is 0. Again, if some element comes here, its again membership value is 0. If I am coming here at this point, so it is a point which is representing some element in the universe of discourse. So at this point the membership value is this one. Here it's a graph, so membership value will be this one. It may be 0.5 or something like that. So I have given you the information. It's a trapezium form of the membership function, which is providing the membership value of the different elements available on the universe of discourse, which we have drawn on the x dimension, x-axis, and on the y-axis we are finding the membership value 1. See here, the maximum membership value of any element of the universe of discourse, it can be 1, and rest all the other elements, they may have value 0 or less than 1 also. So some of the elements here I am showing you a reason. On this x-axis I am showing you some reasons. There is a reason which I am saying is the core reason. So core is a reason in which all the elements which comes in the universe of discourse, they all will have membership value 1. There is one another reason, that is the support reason, and support reason is that reason it will contain all those elements of the universe of discourse which keeps the membership value greater than 0, right? And there is some another reason in this, you are seeing in this membership function there are 2 reasons, which I am mentioning it here as a boundary reason. So boundary reason is that reason where the elements of the universe of discourse, they maintain the membership value which are greater than 0 but lesser than 1. So by this way, in this figure I have depicted you that a membership function which we have drawn in xy plane. On x-axis we are mentioning the different element of the universe of discourse, and on the y on the y-axis we are giving their membership value, and once we are making a function, with the help of that function we are finding the membership value of each and every element of the universe of Discord. So that function makes three different reasons. That functions makes three different reason. So one of the reason is known as the core reason. So core reason is that reason, I'm explaining you again. Core reason is that reason which contains all those elements from the universe of discourse, which contains the membership value 1. And support is that reason which contains all those elements of the universe of discourse where the membership value is greater than 0. And boundary is basically that reason which contains all those elements of the universe of discourse whose membership value is greater than 0 and lesser than 1. So by this way you have seen that there are three different reasons, core, support and boundary. So it's very important as far as university examinations are concerned. So there you may have this kind of questions also, that how many different variety of reasons you may have if you draw a membership function in xy axis, where on y axis you are having the membership value, on x axis you are plotting the different elements over the universe of discourse. They may be continuous, again I'm saying you, or they may be discrete in nature, right? So now coming to the next thing, that is, now here we are saying that the normal fuzzy set and the subnormal fuzzy set. So here I am showing you the membership function in the form of the triangular shape. So as I told you that in most of the scenario you will be seeing the membership function of different fuzzy set either in the form of triangular way or in the form of trapezium style, right? So here I am showing you two figures. In first figure, membership function is again represented with the help of the triangular way. In the second one, again triangular way is represented, but these two figures are different somehow. In the first figure, I am saying that it is the normal fuzzy set A, and in the second figure, you are saying that the fuzzy set is subnormal fuzzy set. So the normal fuzzy set are those fuzzy set where at least one element is there in the fuzzy set whose membership value is 1. So where we are having such a fuzzy set where some of the elements contains the membership value which is 1, that kind of fuzzy set is known as the normal fuzzy set. Here you are seeing that at this point you are saying this is the point where the membership value is represented by this, and here this membership value is 1. So we are saying that this A fuzzy set is normal fuzzy set, and here we have drawn the membership function of another fuzzy set. This is another case. Here again we are having a fuzzy set A, but here we drawn the membership function here, and with the help of the membership function we came to know that none of the elements in the universe of discourse is having membership value 1. So that's why we are saying that this fuzzy set is the subnormal fuzzy set. So now come on the next part. Here we will see the convex fuzzy set and the non-convex fuzzy set. Here we will see the convex fuzzy set and the non-convex fuzzy set. So like you can see here, with the help of two figures I am showing you, I am giving you some of the hint of the convex fuzzy set, convex and non-convex fuzzy set. So in this figure I am writing it the convex normal fuzzy set. So as I told you, the normal fuzzy set will be those fuzzy set in which some of the elements of the universe of discourse will have membership value 1. So here I am showing you that at point x2 element of universe of discourse is having membership value 1. So here some of the element are having maximum membership value 1, so we can say this is the normal fuzzy set. And again I'm saying it is the convex normal fuzzy set. For being convex, there are some properties which must be satisfied. Say we are having a fuzzy set. For being a normal fuzzy set, we know that there should be only one property which must be fulfilled, and that property says that at least there must be at least uh, one element in the universe of discourse or in the fuzzy set which possesses the complete membership value. It means its membership is value is 1. So it is the normal fuzzy set, but I'm saying it is a convex. So now the matter is the discussion is on the convex or non-convex. So convex fuzzy sets are those fuzzy sets where the membership values are strictly monotonically increasing. Once we are moving, we are keep on changing the elements in the universe of discourse, so automatically you are getting the membership value in the increasing way. See here, say for example you are moving here from 0 from this horizon to x-axis. Once you are moving towards x-axis, so there is no way of the minus x-axis. There is no way, because on x-axis we are simply keeping the elements of the universe of discourse. So we have to move only in the positive direction of the x-axis, and we are moving ahead slowly. And once we are moving gradually, slowly on the x-axis, for the different values of the elements of the universe of discourse, you are having the monotonically increasing values of their membership values. So either this condition will satisfy. So if this condition is satisfied, so what does it mean? Say for example, just check the part, this look. Once you are increasing from in this way, automatically you are finding that the membership values are just keep on increasing. They are increasing. If it is happening, so we can say that this is a convex fuzzy set. Or another situation can be, say for example you check the another part of the membership function this side. So now once you are just increasing on the x-axis, for the variety of the different elements which are kept on the x-axis, their respective membership value are in the decreasing way. So the condition is that once we are moving towards the x-axis and we keep on changing the elements on the universe of discourse, rather we can say we are changing the elements in the fuzzy set, their respective membership values, either they must increase monotonically or they must decrease monotonically. So these two cases has been done. Or what may happen, their values they strictly increases and then decreases. If any of these three condition holds, then we can say that the membership function is the convex fuzzy set. It's the membership function of the convex fuzzy set. So these three conditions are either increasing continuously or decreasing continuously or increasing then decreasing. It should not be like that, first of all increasing and first of all decreasing then increasing. It should not be like that, right? Right. So I was just saying that if to ensure that a fuzzy set is the convex fuzzy set, either of the three property must be satisfied. One property says that the membership values of the different elements which we are finding in the fuzzy set, either they are in the increasing way or in the decreasing way, or first of all they are increasing then decreasing. So see here, you can take any three elements here, this. For these three membership values are increasing. If we are taking three elements here, membership values are decreasing. If we are taking these three elements here, x1, x2 and x3, so from x1 to x2 it is increasing, from x2 to x3 it is decreasing. So here third condition is satisfied. So we can say that third condition has been satisfied. So it's a convex fuzzy set. See here, it is another example. So we take three elements on the x-axis, x1, x2 and x3. So what is happening? For x1 we are having some fuzzy value, some membership value. On x2 membership value is decreasing, and then for x3 membership value is increasing. So what is happening here? First decreasing, then increasing. It means we are not fulfilling any of the three conditions. That is why we can say that this fuzzy set is not the convex fuzzy set. This is not the convex fuzzy set. So the last topic of this lecture is the height of the fuzzy set. So the height represents the maximum membership value which an element achieved from the fuzzy set. Say for example, a lot of elements are there in a fuzzy set. So the maximum value which can be achieved by any of the element, that value is known as the height of the fuzzy set. In some scenario, in the normal fuzzy set, height is 1, and in the subnormal fuzzy set, this height is lesser than 1. This height is lesser than 1. I am again repeating, for the normal fuzzy set means the fuzzy set which contains at least some elements for which membership value is 1, and once the membership value is 1, in that scenario their height is 1. And for the subnormal fuzzy set, we did not find any element in the fuzzy set which possesses the membership value which is equal to 1. So that's why we are saying, we are very much sure that in that scenario the height of the fuzzy set will be the maximum membership value of any of the element which has been beared in the given fuzzy set. So certainly that value will be lesser than 1. So that value will known as the height of the fuzzy set. So by this way we have completed all the topics of unit 3. I am also in the full agreement that this unit is very easy, but this makes the solid foundation and background on which you can work for unit number 4. Unit number 4 is very important, in which you will see how fuzzification has been done, how defuzzification has been done, how the inferences has been made, fuzzy inference system has been made, and a fuzzy inference engine has been made. So that was the basic idea. Here in the unit 3 we make a complete picture in a holistic way, where we can use all this information in doing the different kind of fuzzification, then defuzzification, then making the fuzzy inference system and fuzzy engines also. So by this way I am saying good luck for unit number 4, and certainly you will have 20 marks question in your university examination out of unit number 3, and scoring 20 marks question in university examination, it is very easy for unit number 3. So thank you very much. See you soon.